Hello and welcome everyone in this YouTube channel, Mausam Science. Today we are going to learn about the damped harmonic oscillator and to find a damping constant, frequency of underdamping, overdamping, and a critical damping. Okay. Uh, in this video, what we will be clear. Okay, let me make you clear about this. What we will learn in this video, we will learn about the damping. Okay, underdamping, how this underdamping circuit can be made in this physics laboratory. Okay, critical damping and overdamping. Okay, and we will learn about these three types of damping in a detail. Okay, including this, we will learn about the stable micro multi vibrator. Okay, using 555 timer that I will talk in short. Okay, if you want a full video, then I will leave a link in upper I button and the lower description box about a multi-vibrator, because I have made a separate video regarding a multi-vibrator before. You can gain a knowledge from there. Okay, so this is our apparatus. We need a oscilloscope, we need a power supply, we need 555 timer, some resistor, and the capacitors. Okay, I will tell about the detail, what type of what value is needed. And not only this much, we need some other material like inductor, capacitor, and resistor. Okay, resistor, that box type of resistor with several number of pointing switches. Okay, let me talk about the damped harmonic oscillator. Okay, I will come to the circuit diagram of damped harmonic oscillator. Before, we need to generate a stable multivibrator because it gives a square type of output. Okay, for this square type of output, we need a stable multivibrator. If you are provided a square wave signal, then you do not need this type of multivibrator. Okay, but sometime you may not be provided any kind of thing, so make sure the signal is of square wave. If you do not have, then I'm going to talk about the stable multivibrator circuit diagram. Connect 4 and 8 and supply it to plus VCC 5 volt. Okay, and from 8 up to 7 you connect 1 kilo ohm. Okay, that is the value of RA. From 8 to 7 you connect 1 kilo ohm, and 7 and 6 you connect 10 kilo ohm. Okay, color code is brown, black, orange maybe. Okay, brown, black, red, 1 kilo ohm. And you can see here connect 7 and 6 through 10 kilo ohm resistor, and from 6 and 2 you connect each other with the jumper wire. Okay, each other with a jumper wire, and from here you connect 0.1 microfarad, that is 104 capacitor, ceramic capacitor, and take it to the ground. Actually, this is a IC 555. Okay, IC 555. In more detail, if you want to know about this, you can click on the I button or lower description box about a multi-vibrator video. Okay, that gives output, and from 1 number you take it to the ground. Okay, and from 5 number you take a 0.01 microfarad and take it to the ground, that is of value 103. And make sure that you have connected 5 volt and you have connected ground from this power supply. Okay, generally we connect a 5 volt here up and connect this down. Okay, ground down, and this is our IC 555 timer, and these all there are 4 legs on this side, and the 4 legs on the back side. We'll count from here: 1 2 3 4 and 5 6 7 8. Okay, we'll go in this direction. Okay, and these are a simple concept about the legs of IC, and from here 3 number we will get a square type of wave. Okay, the wave will not be like this actually, but it will be in a square type. Suppose this will get a wave in this form. Okay, that is a square wave. If we try to join it, then it will form this type. Okay, the wave may not be actually like this. So this is square type of wave. Now I'll come to here in a damped harmonic oscillator. The generator is set to a square wave signal. We can see here. If there is no generator, we'll set a multivibrator and the output will be square wave signal. The generator is set to a square wave signal that works like an on-off switch. Okay, as I have drawn here, up down arrow before. You can see by making the video backward. Okay, that will give a signal of on off. Okay, that works like an on-off switch. It triggers the damped oscillation every time it switches until the circuit reaches a steady state again. Okay, every time it switches, it triggers the damped oscillation. I have not talked about damped oscillation now. Okay, but it triggers a damped oscillation. Let us remind this thing. Okay, now we'll talk about the underdamping process. What is the underdamping process? It is one of the type of damped oscillation. Okay, there are 3 type of damped oscillation. One is underdamping, another is critical damping, and another is overdamping. Okay, actually, we can see here the amplitude of wave is being decreased along with time. Okay, this is the value of damping. Okay, damping means the amplitude or the intensity of the wave decreases along with time. For an example, if you are playing a guitar, if you toss the string of guitar, it vibrates a lot, and after some time it stops the vibration. If you played a swing, okay, uh, your friend may have pushed you with a greater amplitude at first, and later on the swing becomes stopped. Okay, this is the example of damping. Okay, another, how to remove this damping, we need to create a force oscillation. Suppose in the example of swing, okay, if external force is applied, then we can maintain its amplitude along with the time. If your friend supports you in a swing, after some time, then there is no any decreasement in the amplitude. Okay, that is no any damping condition, that is a forced oscillation. But there is no any forced oscillation, so intensity decrease along with the time, that is called underdamping. Okay, now I'll talk about the underdamping. The condition in which the damping of an oscillator causes it to return to the equilibrium with the amplitude gradually decreasing to zero. When it comes to equilibrium, the amplitude will be decreased to zero. And not only this much, system returns to equilibrium faster, but overshoots and crosses the equilibrium position. This one is the equilibrium position. It crosses the equilibrium position and again overshoots and again crosses and again overshoots and decrease with the time. If I want to draw here something, then let me take this pen. My pen is not working here. Actually, what is the problem? Okay. As we draw a line from here, okay, we can see the line is being decreased along with the time. That means intensity is being decreased along with the time. This is the example of underdamping. Okay. But in the case of underdamping, the wave cross and overshoots, but by decreasing the amplitude. Okay, this is the condition for underdamping. Okay, this is the wave of underdamping. Along with the time, the displacement gets decreased. Okay, now critical damping. What do you mean by critical damping? Okay, in the case of critical damping, the oscillator returns to the equilibrium position as quickly as possible without oscillating and passes it once at a most. Okay, for an example, suppose here we can see the wave is coming down, but it decreases fast. Okay, along with the time, it decreases fast along with the time. Fast decrement, but it do not cross, or if it cross, then it cross only once at a most. Okay, but it do not cross twice and thrice. This is the condition of critical damping. Okay, in the case of critical damping, oscillator returns to the equilibrium position as quickly as possible, but not by delay. Okay, it comes as quickly as possible and passes it once at a most, but it will come in this position. Okay, along with this x-axis. That is the condition of critical damping. Okay, now the other part is, my PDF is not working. Okay, the other one is overdamping. Okay, now I'll read here and I'll compare the critical and overdamping. In this case, the system returns to its equilibrium position without any oscillation, but it takes a longer time compared to the critical damping. Okay, we can see here critical damping is coming here fast. Okay, in the equilibrium position, but here overdamping do not come fast. It takes some time. We can see a time in x-axis. It is taking some time. Here only it is coming. Okay, to the equilibrium position, but it come here in this equilibrium position as fast as possible. That is the condition of critical damping. This wave can be sharp, okay, much more sharp. It can come here only, but it do not cross this and it cannot form under damping condition. Now, till now we have learned about what is the condition of under damping, what is the condition of critical damping, and what is the condition of over damping. How does the wave looks like? We are much more clear about this. I hope so. Okay. If you have any kind of question, then you can raise it in a comment section if you wish. Now this multi-vibrator is arranged. Now we can see here only a square wave, but this do not give such a damping condition. But we need to generate the wave which forms a critical damping, under damping, and over damping condition. Now for this wave will be supplied here. Okay, this one wire we will connect to 0.01 microfarad capacitor. Okay, 0.01 microfarad capacitor is of 103, or you will be given a capacitor of the same size in your lab. Okay, make sure that one wire of this will be connected to capacitor and another wire of capacitor will be connected to inductor. Okay, from here, this output 3 number wire will be connected to 0.01 microfarad, and from here you will connect to inductor of 2.27 millihenry. And the other point of inductor, what we will do, we will connect to the resistor and take the another point of resistor to the ground. Here, what type of resistor we use? We use a variable resistor, okay, like a PO box. Okay, this resistor will be like a PO box. You forget about this other. Okay, and this circuit looks much more complicated, but make sure that from here you are connected to 0.01 microfarad, and from here you are connected to 2.7 millihenry, and from here the other part connect a resistor box and take the resistor box to the ground. Okay, this circuit will be completed. No need to connect this to here. Okay, this ground means ground. Finished. We have one wire over here. This one is a common ground. Okay, but this ground and this ground will should be common, okay, because it should come from this box power generator. So make sure about this thing, whether the systems are connected or not. And I recommend you do not proceed this experiment, otherwise you'll be much more complicated before you get this output in a oscilloscope. Take one wire of oscilloscope, red wire to this 3 number, another wire to ground, and check this as an input. If you get this input, okay, supply this input over here, and after that I will tell you what to take from here. Okay, now this wire, okay, from here we have connected resistor and take it to the ground. You forget about this two line. Okay, now what is this VO? This is the output voltage. Okay, this we will measure with the help of oscilloscope. Now what we'll do, you will use another probe of oscilloscope. There are two probes in this oscilloscope. There is one probe and here is the other probe. Okay, you use other probe of this oscilloscope, one wire over here in this resistor and another wire in the ground, and take the value across value of voltage across this resistor. Okay, now what even you will get this resistor value. After some time we'll change the value and we'll see. Okay, I will tell you. And after that what we'll do, we have got the voltage. Then what we'll get the current flowing through this resistor, that is I is equal to B naught R, B is equal to IL. This very simple concept of Ohm's law. Okay, now if your experiment is totally correct, and if you change the value of resistor from minimum value from 50 ohm, if you start, then you can see the direct value of B naught through the second probe of oscilloscope as a damped oscillator. Can you see here? Okay, this is the real picture captured in our lab. Okay, you can see this type of damped oscillation, and our first experiment will be performed of underdamping condition. Okay, this is the underdamping condition, and the criteria for underdamping condition is you need to start from a lower resistance. Why? The question may be why. Okay, I may come to that later, but at first you need to change the value of resistance from 50, 100, 150, 200, 250, and 300, 350, and see the nature. Okay, this is the experiment. You need to start. Don't try directly from 100 and 1000 and 2000, 3000. Okay, try to take a small steps and see the value of B naught as a damping value. Okay, damping, under damping, critical damping. And I'm sure that if you increase the value of resistance from lower value to the higher value, you will get this type of damping condition. Okay, but let me tell you what I have performed is you need to start from lower value, take a small steps and go to the higher value. But here what I have got in my experiment, the result I'm going to discuss over here, if I take the value of 50 ohm, 100 ohm, okay, 200 ohm, 250 ohm value of resistance, I can see the value for damped oscillation. Okay, that is the underdamping condition. But if I move to the value near 1000 ohm or 1 kilo ohm, then I can see the conditions like a critical damping. But if I move further from 1000 to 5000 ohm, okay, then we can get the condition for overdamping. One thing, okay, what I have feel in our practical lab, I'm going to discuss over here, this rheostat may have some error. Okay, because some I have found in my lab that if I take out a 200 ohm resistance, then this resistance box shows infinity resistance, because there is a gap, because the instrument is too much old. So make sure that the resistance box is working very well. So for that you can connect a multimeter to this resistance box, another wire, whatever. Okay, don't I want to draw here something, because I have faced this type of problem. Okay, this setup is okay, but this is a multimeter. Set the multimeter to DC value. Okay, because we are supplying a DC voltage, and what happen is from here you measure this resistance, no DC, but take it to the resistance measurement area and connect this two wire to resistance value. And you see whether you remove the wire of plug of resistance, there should be a value reading, okay? Because I found this type of error in this device. Sometimes what happen, if you take out a 200 ohm resistance, you will see a critical damping. That is not good according to our theory. But according to this resistance box, the resistance is infinity. It's also over damping condition or critical damping condition. But there may be some error. There may be misconfusion with the students. So you can measure this thing. Okay. I'm sharing my knowledge with you all. Okay. What problem I faced in the practical lab. So I want to go further. Now, little bit explanation I will see here. Okay. Um, this one number is of frequency, okay, the input frequency which is given by the stable multivibrator, okay. What type of frequency of wave it gives as output, we can calculate by this 1 by 2 pi into 0.693 Ra plus 2 Rb and C, okay. This is the condition. Now Ra and Rb we have got over here, okay. Ra and Rb value we have got, and we will see this value. And one more thing I want to tell you, that this is the example of stable multivibrator, and the outcome of this stable multivibrator may not be, okay, I repeat once, the outcome of this stable multivibrator may not have an equal time period. Suppose this may be long, this may be short. So for that, we worked a little bit hard to change this resistance, because stable multivibrator have 1 kilo ohm resistance, no doubt. But if you want to change this time period to a equal and get a square wave, then we need to connect here 1 kilo ohm and 10 kilo ohm in a series. Okay. Oh, sorry. 2.2 kilo ohm and 1 kilo ohm in a series. 2.2 kilo ohm and 1 kilo ohm in a, sorry, not series, parallel. Join this two wire of 2 kilo ohm and 1 kilo ohm. Okay. Join this two wire and join it over here. Replace this. Okay. Replace this. Okay. Simple. Join two leg and connect it. It will be in parallel. And if you want to know this value, connect a resistance multimeter and find out. Okay. You need to get here a square shape. Change the Ra, keeping Rb constant. Okay. No matter, I have made you clear. Hope you will understand it. Okay. Please don't leave the video in middle so that the information will be made clear to you all. Okay. This is the input frequency. Now this input frequency will be supplied to this two number circuit. Okay. Figure number 2. And what happen is using a Kirchhoff's law. Okay. The input voltage here is E naught. Okay. That input voltage will be dropped in this capacitor, in this inductor, and in this resistor. Okay. Now, what type of voltage will be dropped in this inductor is di by dt. Okay. What type of voltage will be dropped in this resistor is B is equal to IR. We know this. And what type of voltage will be dropped in capacitor, Q by C is equal to E naught. That is the total voltage. Now, if you take a time derivative of this equation, we'll get this equation. Okay. Derivative. Okay. First derivative will be second derivative. I will be di by dt, and Q by T means actually a current. Okay. Flow of charge per unit time is current, and divided by C is equal to E naught is constant. So it will be 0. Now, from here, we have a trial solution. I is equal to I naught e power mt. Okay, it is a trial solution for value of I in this experiment. So if you put the value of I over here and do a derivative, we'll get this equation 3 in the form of this equation. Okay, in the form of this equation. But let me talk about this equation 3 once. Okay, let me talk about this equation 3 once. If we remove this second number 1, okay, this r di by dt, then this first and third expression of this equation makes it as a linear harmonic motion. Okay, simple harmonic motion. It will take this equation to simple harmonic motion. If you cross this one, okay, if you cross this part, then it will take to a simple harmonic motion. This video may be a little bit longer. Okay, if I cross it, then this two equation makes it as a simple harmonic motion. But if you make a presence of this one, there is a resistance, so it converts this simple harmonic motion to a oscillation, damped oscillation, by changing the value of r. So there is a little bit trick in this equation. Okay, this equation is the main heart of this experiment. There is the value of r, so we will be more focused in this equation number 3. Okay, now furthermore, if we apply the value of this I is equal to I naught e power mt in this equation, so we'll get this equation in the form lm square plus rm plus 1 by c is equal to 0. From here, if you want the value, measure the value of m, you will get this one. Okay, now we'll suppose this minus r by 2l as a alpha and this value as a omega. Actually, this alpha is a damping factor, okay, damping constant, and this omega value will be this much. Now we need to calculate the underdamping condition. As I told you before, I found critical damping at the range of 1000, overdamping at the range of 5000, and underdamping below the range of 1000 ohm. Okay, I have found the value for resistance over here. Okay, the first condition is underdamping condition where the omega value is greater than 0. If you keep this value greater than 0, okay, root will be cancelled and you will get the value of R is equal to less than 2 root over L by C. L is the value of inductor and C is the value of capacitor. Apply the value and get the value of resistance, below which resistance you can fill the underdamping condition. This is the theoretical value, but and in your experiment there may be some type of error, so that's why get the actual data from the experiment value by taking a small steps of this resistor from 50, 100. Okay, at what point the damping stops, that is the value of resistance, that is the boundary line of resistance below which we can get this value, match it with the theoretical value and get your error. Okay, under damping condition finished. Now, similarly, critical damping condition, omega value will be equal to 0. Omega means this. If you keep this value equal to 0, you will get this condition. L is the measure of inductor, C is the measure of capacitor. Find the value of R. Okay, around that value, at the value of R, what you have calculated here, you will get the value of critical damping. Okay, compare the experimental versus theoretical value. This is theoretical value, and you change the resistance. Okay, and get your value, okay, of critical damping. Similarly, overdamping, if omega is imaginary, then if R value is greater than 2 root over L by C, you will get the value of overdamping. But okay, the most thing is you need to control this. Theoretical value you need to calculate, and experimental value you need to get it from here 50, 100 to 50, or you can take 100, 200, 300, 400. It will be easy, less time consuming, and you will get the nature of graph here. Okay, don't be in hurry. Before 1000 ohm, you will get here this type of underdamping. Around 1000 ohm, you will get this type of critical damping in a short period of time, peak. Okay, and around the range of 5000 you will get this overdamping. Okay, you calculate this value. I should not say 1000, 2000, and 5000. Okay, get this value and find the nearby data at which you will get this. Okay, in this experiment we have learned the circuit diagram of connection. Okay, and how to get this graph, actually how our graph is being changed, and what is the damping constant, and underdamping, critical damping, and overdamping. This experiment is quite long, so it is taking some time. So feel free to know. Okay, if you have any type of comment, leave it in the comment box. We'll meet again. Bye bye.